Hey guys, welcome to week 5. So this week we're steering away from rocks and we're taking our first look into the solar system. So this one's really exciting for me. I don't know if anyone else feels that way, but I've always been quite interested in the planets and the moon and all of that general universe stuff. It really blows my mind. So probably my weird fascination with science fiction, nerd alert. So let's take a look at this week's topic through a classroom lens. In ACARA, the solar system is first introduced in year 5. So it's a little bit later in the primary school years. The content descriptor is the Earth is part of a system of planets orbiting around a star, which is our sun, of course. One of the elaborations is particularly important for our experiment that we're going to be doing today, and that is modelling the relative size of and distance between Earth, other planets in the solar system, and the sun. Now, although it is specifically introduced in grade 5, the curriculum really builds up to this overarching concept from foundation year. So it steps us through seasons, Earth's rotation, axis, and then really lands here with the solar system in grade 5. Now, in textbooks and posters, often the distance from the sun and between planets, it's not really correct and really doesn't do the scale justice. So kids in the classroom will, I think, be really blown away by this activity once they understand the true scale of what we're looking at, especially how big the sun is. So today's activity, we're going to do just that. I have a lot of awesome props with me, which I'll show you in just a moment. And we're going to take actually an adventure down to my local park as well to do a bit of a grand scale experiment. So all exciting stuff. What we're going to be doing is determining the distance and size of the planets in a small section of our solar system. Now, I'll action the activity at a grade 5 level. However, the complexity, of course, can certainly be increased for high school students and also simplified for lower years too. So high school students really could actually calculate these distances. Now we've got them here ready for us and things like that. But high school students, this could be a really good opportunity to do some maths and also incorporate the science skills in there and also research into the planets too themselves. And of course, we can use smaller spaces and items like witches' cones and things like that to make the experiment simpler for our littlies. So before we get too ahead of ourselves, let's have a look at our research question for the week. So I have popped this one in here. In relation to the sun, how far away are the planets in our solar system and what effect does this have on them? Does everyone agree? Everyone happy?
Yeah, that sounds good.
Perfect. Okay. So this week's experiment is an observational modelling exercise. So there's actually no hypothesis as such, or the cows move softly, no variables, etc. What we will be doing though is still predicting and estimating, but we'll get to that in just a moment. Let's have a quick look at the materials we're going to be using today. So I've got myself here, there's quite a lot of them, so enjoy this. I've got a large piece of paper, so this one's A3. I've got some small post-it notes here. I've got a 30 centimetre ruler. I've got a measuring tape. Now, that's in my pack to take to the park, so I'll show you that in just a moment. I've also got a 30-metre red rope. I've also got a tarp, a peppercorn, a blueberry, a watermelon, a grapefruit, an apple, a lime, and 2 cherry tomatoes. So very mysterious, very exciting stuff. But I'll get to all of those and what they indicate in just a moment. So look, the larger experiment will be conducted in the park, and we have fruits. We have risks involved with going outside. So let's have a chat about health and safety. Darcy, do you want to start us off with maybe something that you've considered with health and safety?
Yeah, so I think that definitely, like you said, we're working with fruit, so that's food. We could be dealing with like some food allergies. So those students that do have food allergies may need to wear gloves and appropriate PPE so they do not come in direct contact, or they might just not have to actually be touching any of the fruit at all and maybe just be observing just to keep everyone safe. I think what the teacher would actually say in this situation would be it's important to educate the children and family members about these food allergies. So information can be sent home prior to asking students to bring in fruits for the activity so the families are aware of what's actually happening. The teacher would say something along the lines of, hey students, what would you do if I was having a reaction after touching the fruits? Students can like brainstorm ideas and recall to teacher what the specific action plan is for students with those types of allergies, and just discuss those things so they're well aware.
Yeah, really important stuff. Alicia, have you got anything you wanted to add?
Maybe just about kind of spatial awareness, because you're going to be going to like a big area with the kids. So maybe like that could lead to some behavior issues potentially. So maybe like you might want to separate friendship groups, or just think about the children you have and certain things you might want to implement. As a teacher, maybe the teacher could get the students to write down some ideas of how they can be safe in a big open area, just so it gets them involved, and they can all agree on it, and the teacher can remind them as they're out there, like, you know, what'd you come up with, remember what you said, and just to keep everyone safe.
Yeah, nice. I totally agree with that. Jenna, anything you wanted to add?
I think if there's no safe space to complete this activity, then it would be appropriate to keep it to a scaled back version within the class parameters.
Sure.
Like in the first section of this experiment that we're going to do, where we do it in the 30 centimeter measurements, that could be more appropriate for the classroom, and it still provides beneficial learning, but with limited risks. Also taking into account what time of day this activity is taking place. For instance, it's not ideal to do it in the middle of the day when it's super hot. That's not exactly safe, especially in the middle of summer in Queensland. So when going outside to the oval, the park, we need to ensure students are wearing appropriate uniforms, so like their hat, and take their water bottles with them as well. I think the teacher will need to like pose questions to the students, such as, can you think of some reasons why it would not be safe to go outside and do this experiment? And getting the students to think about their own safety as well as others. The teacher can also prompt them by giving them scenarios to gauge whether they are aware of the risks. For instance, if we go outside to the oval, or your sheet or your materials blows away, what is the other side of the fence that's dangerous? What's on the other side of the fence that's dangerous? Like maybe cars, that kind of thing.
Good point.
It's more effective if students can point out these safety issues on their own, or with guidance from the teachers, as opposed to just the teacher telling them what could go wrong.
Absolutely. That's an actually really excellent point, I think, with the cars. I suppose we don't think about that as much, but they are generally around and just on the borders of the school. So yeah, really good point. Rebecca Loda, what do you think?
Well, I guess something that we don't think about as much, but like slips, trips, and like falls, obviously there's some physical hazards involved. Obviously, you know, for us to do the experiment, we are, you know, obviously adults, so lifting heavy objects such as like watermelon and things like that isn't as big of a deal to us. But obviously remember, this is to go in the classroom, so we've got little students trying to do these sorts of things, so it's important that we teach them you know, the explicit safe handling practices, you know, so they don't, you know, simply as trying to pick it up and dropping it on their foot or something like that. Another way maybe could be that it's already set up down there, so all they have to do, it's already been set up prior to us going down there, and it's just a matter of them moving it along the scale to see where it lands. In another thing could be also as well, like with the the sheet and the tarp and the rope and things like that, that can become a safety hazard as well if it's not obviously, you know, tied down. If, you know, there's lots of different people moving up and down and trying to, you know, fit into the same space, that can become a problem. So I guess probably something that the teacher would explicitly do is, you know, get some of the students to practice and demonstrate some of the techniques, so that they know that they're definitely going to be able to do that on their own when they head down there, because obviously the teacher's going to monitor you know, everyone's behavior, and is going to be moving around and making sure that they're all keeping on task. But, you know, we do need to have that trust that they can follow instructions and do those kinds of things. Another way we could do is, you know, to make sure that we could get students to point out what are some ways that we can make sure that our space is safe to work in. And then they might suggest setting up boundaries so that only one person's measuring at a time to avoid disorganization and things like that as well.
Yeah, for sure. Like really great points there. I think that it's so important for this one because it is outside to really consider these things. So good work, guys. All right, so let's get into some activities. Good fun. Our first activity that we're going to be doing, I'm just going to get you guys to have a little bit of a think. So when you were at school, now I didn't have one, so I'm hoping you might be able to think of one. Do you remember maybe something that you learned to remember the planets and what order they went in?
I didn't have one at school.
Neither did I.
No, I really didn't. I mean, I've got one now because I've looked into it, obviously.
Yeah.
But I didn't have it. So maybe this is something unique to kids now. Maybe obviously the Australian curriculum has changed.
I feel like it would definitely help too if I had a little jingle to remember. Like I would have really loved that, you know, an easy way to just, you know, remember those fun facts.
I totally agree. I will tell you what I have, my little one that I've discovered. I won't tell you exactly the planets yet. We'll get to that in just a minute. But mine is my very energetic mother served us noodles. So that's the mnemonic I think that I have. It's a little bit crazy. Now
I like it. Yeah. I'm just trying to think of what those planets connect to, like what the.
Well, I'll tell you. So what I'm going to actually do. Okay, so I'm going to do this little activity where I'm going to show you some fruit. Now, they're all different sizes. I'll just run you through because some are really, really small, so you might be able to see. I'm going to show you some fruit, and I'm going to get you to guess which planet they are. Now, before we do that, I'll now tell you what the planets are, obviously. So we've got so that would be Mercury, we've got Venus, energetic. Anyone know what the E would be?
Earth.
Hey, good stuff. Home, nice easy one. So my very energetic mother. So we've got Mars, just Jupiter, served Saturn, us Uranus, noodles, Neptune. So what I'm going to get you to do is have a little look at these fruit and try and guess which one represents, I suppose, which one. What do you think? So I'll pop this over here. Now, sorry, this could be a little bit awkward. Here we go. Oh, just dropped something off the table. Lovely. Okay. Now, also, just for a heads up, this was too heavy for me to put on here as a whole. I'll show you. We're looking at this. Now, when I go to the park, I do have a big one, but it was so heavy, I couldn't put it on this little table. So we're going to work with this half.
That's
obviously that's a good
cool.
thing to point out for our kids as well. Obviously, you know, if we're struggling with that.
I know it's actually
and might be dangerous as well, really.
I know. I was a bit shocked at how weak I was when I tried to lift this watermelon. So I need to hit the gym a bit more. Okay, so these are our fruits. Now this is the smallest. This is a peppercorn.
Oh my goodness.
Wow.
Quite tidy. I've got now, again, blueberries were not at my local store. So I thought that this piece of blue tack was quite relative to the size of the blueberry. So we're going to pretend with our imaginations. That's a blueberry. We've got 2 cherry tomatoes here.
Yeah.
Nice.
We've got a lime, a grapefruit. We've got our watermelon, pretending that's a whole one, and a green apple here. So I don't know. I'll go through them and I'll see which ones you think. I mean, does anything stand out to you straight away as a guess of which one you think it might be?
Well, I know that, I think Earth and Venus are relatively similar in size. So I'm thinking that they would be the cherry tomatoes.
Ooh, I like it. Good.
Since
Okay, so what I'm going to do is I'm
them.
going to put a post-it note on the ones we guess. So we're saying the cherries are cherry tomatoes, are Earth and Venus.
Venus, yeah.
Okay, everyone agree? Everyone happy?
Yeah.
Yeah.
All right, what about the line? Do we have any idea for the line?
I don't know.
Could it be Neptune?
Oh, we'll have to find out. Let's have a look.
Yeah, I
Is
don't
everyone happy
know.
with that Neptune, or anyone controversial want to get involved?
It could be Neptune or Uranus. I don't know. Uranus.
Oh,
Ooh. All right.
what do you
well,
think, Beckel? Beckel,
Yeah.
do you think it's Neptune or Uranus?
I'm going to go with Uranus for this
All
one.
right.
All right, let's do that then. Sorry, Darcy.
That's fine.
Obviously,
Any rules,
once
guys?
we get a bit more about it, we can sort of,
Yeah, you'll know pretty soon which ones are right. Okay, what about the peppercorn? Do you have any idea about the peppercorn?
Oh, it's the smallest.
Mars or Mercury?
the
Mars,
tiniest one.
maybe? Yeah.
Yeah.
Controversial.
Or maybe
Mars,
something,
maybe?
if we relate it sort of back to that little catchphrase, it's going to be sort of maybe something
Oh, I like
With
that.
one of
Using
the-
prior knowledge.
with one of the
Oh.
M's, because that was one of our first ones. So maybe
The first one? Yeah.
maybe Mercury, yeah.
Everyone happy?
Yeah. Sounds
All
good.
right. Okay, Mercury. Now it's not going to fit on my peppercorn, so I'll put it right next to it. All right. So watermelon. I don't know if this one's easy or not. What do you think?
I reckon definitely Jupiter. Jupiter?
I think Jupiter, yeah.
Yeah.
I know that from prior knowledge that Jupiter's big.
Yeah.
That is
Yeah.
big.
Yeah.
Jupiter it is. Grapefruit.
Well, it's got to be Saturn. It's the longest
Yeah.
one.
We'll see. We'll see.
Yeah.
Quite a size
Okay.
difference.
Yeah, for sure. Okay, so we've got the blueberry,
Oh, we've got one
blueberry,
more.
Oh,
and
no, we have
also
two
the green
more.
apple. Yeah, green
Oh,
apple
sorry.
and the blueberry.
What's left?
The green apple
Mars and Neptune.
and the blueberry, and yes, we are missing Mars and Neptune.
Well, I
would-
think the
the blueberry is Mars
yeah.
Yeah.
and the
And
apple.
so,
Yeah, I agree with that.
all right, nice work, guys.
I'm gonna put this into a table as well about like I'm gonna record our predictions as well so we can see
Excellent.
Good idea.
See how we
Yeah,
go.
how
great.
correct we were.
Yeah.
No, it's actually an excellent idea because, yeah, they'll be able to help us make some patterns,
Yeah, it'd be
maybe, and have a
interesting.
look at what's going on.
Yeah.
Okay, so we've all had a little guess
Mhm.
about what we think. Now, we were pretty spot on, actually, guys. The
Oh,
only
nice.
thing that we had wrong was no, I think we got it all right.
Oh,
No, okay, we got the lime and the apple mixed up.
Oh,
Ah.
so close.
dang.
I know, but everything else.
But it's all a
Nice one.
learning curve. It's all, something. It was
Yep.
quite
Yeah.
fun to get involved.
I know. So what I'll do is I'll put these now in the actual order they go in, and we can have just a quick look. So we start off with my Mercury, our peppercorn, very small. Now this is going to be flipped, I think, for the Zoom purposes with the mirror image. So just go with me. Mercury, my very, so we've got Venus here with the cherry. Energetic, we've got Earth.
Mhm.
Mother, Mars with the blueberry.
Okay.
Just, we've got Jupiter with our big watermelon. Served,
Wow.
so Saturn. Oh, this is not going to fit, so I'm just going to have to do it. Served us with Uranus and Neptune noodles. So I'll just pop this here. Make it spread out a little bit. There we go. And there you have it.
Wow.
Oh, cool.
Wow.
I'm pretty
Very
impressed that
cool.
we did pretty good apart from
Dang.
the apple and the lime, but I'm pretty
Yeah,
impressed with us
definitely. It's
otherwise.
You are, so yeah, we did well.
pretty awesome, guys. I'm going to take a photo of this to send to our data girl.
Yeah, great. Thanks.
No problem. So I'll send this photo over. And I'm very impressed with our estimating and predicting skills. Cool. Awesome. Okay. So I've got them in the right order now. Now, let's have a quick think about what do you think now we know these sized items? What is something around the house that you think could maybe represent the sun?
Oh, it
A
would have to be
big
big.
carpet.
A big what?
Carpet.
Carpet.
A big couch. A car.
Yeah,
Sounds
good
like
one.
A car, yeah, that's a good one.
Not a bad one.
A truck.
A truck.
A truck.
Gosh.
Have to think about
Amazing.
something that we'll
That's
all have.
Yeah, something around the house. Something around the house.
Mm.
Maybe a
But no, what I like is that you guys can understand that the sun is ginormous compared to obviously the planets. So even though we've got a big watermelon as Jupiter, the sun, it could be still the size of a car. I will actually show you proportionally the size of the sun soon enough.
Wow.
But we will get to that shortly. All right, guys, so we're going to hit activity 2. Now, this one here involves our paper and our ruler and a pen. I will show you where we're going with it in just a moment. So I'll pop it down here so you can see this paper. Now I'm going, let me just make sure that this is, sorry about this. Okay, gorgeous. Now I'm going to be drawing a 30 centimeter line. Okay. I'm just going to pop it in highlighter to make it a little bit brighter for you guys to see. Lovely. Everyone see that okay?
Yep.
Yes.
Yep.
Excellent. Now, I have here a little representation of the sun. Now, this is just a tessellation block. And I've got my, representation here of Neptune. So that's the very end planet. So we've got the start and the finish line here, basically. What I'm going to get you to do is just have a little think to yourself. Where do you think the planets would sit on this 30 centimeter scale? So if we've got 30 centimeters, do you think maybe Jupiter sits at 20 centimeters? Do you think maybe Mercury sits at 1 centimeter, 6 centimeters? So it's just about sort of your understanding of where maybe they sit in this scale. So take like 15 seconds or something like that, just to have a little think about it, jot down some ideas, and then we'll come back and we'll have a quick think about it. Cool. Awesome.
Awesome.
Cool. Okay. Cool.
Yep.
All right. Awesome. So we've had a little think. Let's have a start at Mercury. So where do we think on this scale Mercury would sit? How many centimeters along from the sun? Any ideas here?
I think around 5 centimeters.
I was going to say
is my
5
guess.
I was gonna
Yeah.
say like 4 or 5.
Yeah.
Okay.
So
Are we
it's going to be at the start.
thinking
that-
maybe 5?
Yeah.
Yeah.
Right.
All right, let's lock in 5.
Okay, I'm popping it here, and I'm just going to put our little post-it note from our fruit on there for
yeah.
Cool.
future reference, if I can find it. There it is. Sorry. Okay, Mercury. Where do we think Venus would sit on the 30 centimeter scale?
I feel like
7 or 8 or 9 or.
Yeah, well, it was still quite.
Yeah, maybe
Yeah. About
maybe
7?
7.
7,
Yeah.
yeah.
7?
7, yeah.
Okay. Nice. So we've got 7 here for Venus. How about home? How about
Well,
Earth?
we know that they're, a bit close, like quite close together. So maybe 10 centimeters.
Yeah.
Yeah, 10, 11, 10, I reckon, yeah.
Then? Cool.
Yeah, 10.
Now we've got Mars next.
that's also close. So
12?
12.
Yeah, 12.
Oh yeah, nice and close. So these ones are quite, in a row here.
Yeah.
Okay, so we've got Jupiter next.
Which is not as
Probably
close.
Yeah, probably a bit of a jump, I reckon, between those measurements.
So what,
Maybe like
19,
just
18?
12 to like,
yeah, I was gonna say around 20. So yeah, maybe a bit
I-
less than 20.
I was like
18?
less than 20.
Yeah.
Yeah, so around 18.
18.
All right, 18 it is. So we're going to pop out of here. So yeah, a bit of a jump on this one. Okay, and then what about Saturn?
That's quite close still, isn't it?
It's like around 20 then, do you reckon? Around 20?
Maybe,
20?
yeah, maybe,
yeah, 21.
maybe a little bit further away, like maybe 21, 22.
Yeah.
Yeah, I think 21.
Okay.
Okay. Everyone happy with 21?
Yeah.
Yes.
All right. Now the next one is, of course, Uranus. Because we've got Neptune already on here at 30. So
Ooh.
Uranus. What do you reckon?
Probably maybe
I think
28,
or
maybe,
maybe-
like towards the
Yeah.
upper end of the scale,
Yeah.
I was gonna say yeah,
Yeah.
over 25.
29.
close
definitely.
to Neptune, that sort of way up that end of the scale.
26, 27.
I'd say 28.
Yeah,
28.
yeah, I reckon
Okay.
Okay,
Look-
let's do 28.
Okay.
Lock it in? All
Yep.
right.
Yeah.
28 it is. Cool.
That means.
All right, and then we've got
Neptune is
Neptune there
30.
at 30. Nice work, guys. Great estimating. Okay, so the next part, I'll just pop it back on myself. Okay. So the next part of the experiment, we're actually going to go outside. So what I'm actually going to do is we're going to pause the video. I'll get outside because we can't be together because we're in COVID restrictions.
Yeah,
So I'm going to go outside on my own.
Mhm.
Unfortunately, which is very sad. But it's also something to consider with the kids as well and safety. We
Yeah.
can't be together, so we've got to improvise a few things here.
Mhm.
So what I'm actually going to do is I'm going to go outside on my own and I'm going to do this then at the park. I'm going to film it. We'll come back and we'll actually just insert it, I think, into the video just to make things a little bit easier. So I'll pop it in the video and then we can have a chat about what happens after it. So we'll
Sounds
see you on
good.
the other side.
Okay, cool.
All right.
Great.
Bye.
Okay, guys, so I'm down at the park. We've got our 30-meter setup going. I've got our estimates that we've just done. I've popped them on a bit bigger pieces of paper just so that we can see them a little bit easier along our line. So I'll just show you some of the equipment I've set up already. I've got the sun behind me. Now the sun I've made out of a tarp just because of the boggy ground. We've had a bit of wet weather lately. Made it 2 meters in diameter. I've also got here our 30-meter rope, so I've popped it in red so it's a little bit easier to see. So that starts here at 0 meters, and that's going to go all the way down to the 30-meter mark down the end. So what I'll do is I will pop all of our estimates along the line to see how it all looks, and then we'll go from there. All right, guys, we're going to put out our estimates, and every single one, I'll let you know what meters we estimated, and just keep sun safe as well. That's all we need to do at school. All right, let's do it. We got Mercury, 5 meters. Got Venus at 7 meters. Got home here at Earth at 10 meters. Mars, 12 meters, apologies. Okay, Jupiter, a bit of a jump at 18. Saturn, 21 meters. Uranus, 28 meters. Oh, there's a big one. And last we got Neptune at 30. All right, we'll do a big shot now of the whole lot.
Okay, cool. So I've got them all laid out to what we estimated. What I'm now going to do is I'm going to go grab some fruit that we talked about earlier, and I'm going to actually pop it out as the actual distance from the sun of each planet. So this one will actually be the proper meter distance, and I'll do that now for you. All right, cool. Just to refresh, we had some fruit here that we established were going to be the relative size of the planets on our scale. So just a refresher, we've got Mercury here as our peppercorn, very small. We've got Venus as our cherry tomato. Got Earth as a cherry tomato as well here. We've got, what have we got? Mars is the next one. So Mars didn't have a blueberry, unfortunately, so we've got ourselves a blueberry-sized piece of blue tack. We jump up to the watermelon, which is Jupiter. We've got the grapefruit as Saturn. We go to Uranus, which we've got an apple, and then Neptune at the end, so we've got a lime. So just to give you a bit of a look at it, because when I put it out on the grass, it's actually quite hard to see. So just thought I'd give you a quick view before I go and pop them out at their distances. So I'm going to go do that now, and then we'll come back and have a chat about it. Okay guys, just doing some really serious calculating here. I've figured out all of the distances relative to the sun here, and I've got the fruit ready to go to put out to show our real distance from the sun compared to our estimates. So our estimates were a little bit off, but that's okay because that's the point. What we'll do is I'll go along, I've got all of my fruit here in my pockets, and I'm going to show you how far they are along our 30 meter relative scale. Okay, so we've got our sun here, of course. Now, our first one is actually here at 38 centimeters, and that's Mercury. So that's represented by the peppercorn. So I'll just get that out and pop it here. So 38 centimeters. A little bit off what we had out there at 5, but anyway. The next one we have here is Venus. Now that is represented by our cherry tomato, and that is at 72 centimeters. Okay, so next we have home, which is Earth, again represented by the cherry tomato. Earth is at 1 meter, so we'll put that here. Alright, so we've got Mars here at 1.5 meters. Now Mars we've got represented by the blue tack blueberry, so I'll pop that here. Okay, we're going to go for a bit of a jump now. So the next is to Jupiter. Now Jupiter is out at 5.2 meters, so I'll go out there. Okay, so we're here at Jupiter. I'll get our trusty assistant here. Thank you. So a little bit bigger to our other fruit so far. This one here is at 5.2. Now to give you some idea of how off we were, we have here on our estimate Mercury. So a bit wrong, but that's okay. So we're going to go to Saturn next at 9.5 meters. So just get my trusty assistant, thank you. Okay, so 9.5 meters here for Saturn, and modeled by our grapefruit. Okay, this is where things really take off. We're going out now 19.2 meters. So out here we have Uranus, modelled by our green apple, out at 19.2 meters. So I'll pop it here. Again, as you can see, we were a bit off. Here is our estimate for Jupiter. So I'll pop this here. And then the last one is actually out at Neptune, which is all the way at 30.1 meters. So I'll take that out there now. So that was modeled by our lime. As you can see, we were a bit off with our estimates. but I'll take you through each one as we go along in just a moment, so that our CDSU girls can actually explain some of the different concepts behind these planets and their relative distances from the sun.
Okay, so I'm back from the park. Had a little change of outfit, but we're back and we're ready to start chatting about some of our results. So I've got Jenna here, who's actually going to chat about graphing data and our results. So I'll pass it on to you.
Yeah, so what I was thinking is, so I have some tables here and that have our predictions in them, and also the correct fruit and the correct distance with our first two activities that we just did. But I was just thinking it might be a good idea to hear what Alicia and Darcy have to say about the CDSU, so that we can do another table or another graph that shows us a bit more of a pattern in like why the differences in these planets in relation to their distance. I think that would be beneficial. What do you guys think?
Awesome.
Yeah,
Yeah, for
definitely.
sure.
And then we can
Sounds
review.
We
good.
can understand those links.
Yeah, and then we can look at all the different data that I have.
For sure,
Does
because
that
we've
sound
seen
okay?
the basic pattern, like when I've gone out to
Yeah.
the park, we can see,
Yeah.
you know, basic, you know, which one's in order and the distances. That's easy
Yeah.
enough. You can show that
Exactly.
graph, but to get a more solid information, I think, yeah, I agree.
Yeah, I think
CDSU.
yeah, cool. So Alicia and Darcy, if you guys want to educate us.
Totally.
Yeah.
Excited.
Okay. So in the universe, there are many planetary systems like our own. Ours is called the solar system. This is because our sun is named Sol, which means sun in Latin. According to NASA, the solar system was formed around 4.5 billion years ago as a result of a dense cloud of interstellar gas and dust collapsing. This is predicted to be in result of an exploding star in close proximity called supernova. This explosion caused a solar nebula to form, which is a spinning disk of material. The solar nebula attracted more materials, and eventually, with a combination of hydrogen and helium and a vast amount of energy, the sun was created. Our planets arose from matter clumping together around the sun with individual gravity pulls, shaping large clumps into spheres, creating planets and moons. The solar system consists of a star, which is our sun, various planets, Mercury, as we know, Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune, plus dwarf planets, which are Pluto, and there's also over 150 moons in our solar system. Out of these 8 planets, Mercury and Venus are the only 2 without a moon in their orbit. The bigger planets, such as Jupiter and Saturn, attract the most moons, and it is said that the moons in their individual orbits similarly reflect the solar system, as there are multiple moons orbiting around each planet. And the closest planet, as we know now, to the sun is Mercury.
So Mercury is the smallest planet in our solar system and the closest to the sun. It is only slightly bigger than the Earth's moon, meaning it is about 1/3 of the width of Earth. It is also roughly 58 kilometers away from the sun. It is an interesting planet temperature-wise as well, because although it orbits so closely to the sun, it's actually not the hottest planet. It has a very varying difference in temperature as well, going from as cold as minus 170 degrees Celsius to as hot as 430 degrees Celsius. The way that Mercury orbits the sun is strange as well, as it rotates on its axis 1.5 times for every time it orbits around the sun. Due to the highly elliptical path of orbit, its seasons and climates vary considerably during the year. This, in conjunction to having no protective atmosphere at all, the sun has a high influence in its conditions, meaning it gets extremely hot during the day, however, very cold at night. In regard to its landscape, it has very large crater impact on its side, which is called the Caloris Basin. Directly opposite to that crater, there is a large area where there are shock waves which converge and form an area called the weird terrain. Mercury is also mostly made out of iron, and due to its percentage of core being iron, scientists believe that it was actually hit with an object in its early development stages, which dislodged any materials on its surface, leaving it to just be its small iron sphere that it is today. So that's quite interesting. Mercury also has long curved ridges, which are called lobate scarps. These are like cliffs and they look like wrinkles on the surface. And that's actually caused by the slow cooling of the iron.
There you go.
So second closest to the sun is Venus, sitting at over 100 million kilometers away from the sun. Surprisingly, despite being the second closest to the sun, Venus is the hottest planet in our solar system. This is due to the thick carbon dioxide filled atmosphere that is paired with a shield of yellow sulfuric acid clouds that withhold the heat in the planet. Due to the atmosphere of Venus, the planet sits at a boiling hot temperature at the planet's surface. The average surface temperature of Venus ranges from 430 degrees to 480 degrees Celsius. This is hot enough to melt lead, so very hot. Now, because of this temperature, all water on Venus has turned dry because of the heat. It's just evaporated almost instantly. All water that was once on Venus has now boiled off into the atmosphere. Venus has an extremely forceful air pressure that is far more than that on Earth. The air pressure on Venus is compared to the pressure felt over 15 kilometers below sea level, so very intense. The surface of Venus is mountainous, filled with valleys and thousands of volcanoes. The planet has two key areas. Ishtar Terra, which is similar to the size of Australia, and Aphrodite Terra, which is similar to the size of South America. Venus is covered in large craters, all larger than 2 kilometers in diameter, so very big. The reason for this is because of the dense hot atmosphere so it burns up all the small asteroids, so only big asteroids are able to get through and impact the planet. The size of Venus is similar to that of Earth, and it is a common phrase actually to refer to both the planets as twins, but clearly, despite size, they're very different from each other.
Yes, they're definitely very different. So Earth is obviously a planet we're very familiar with. It is our home planet, and it is unlike any other. It is the only planet in our known universe to be able to host life. It is the 5th largest planet in our solar system and only planet to have liquid water. It is roughly 150 million kilometers away from the sun and the 3rd closest. It rotates on its axis every 23.9 hours. So that's what 24-hour daytime is, giving us day and night. It is also tilted 23.4 degrees away from the Earth. It has a 23.4 degree tilt away from the sun, which gives us seasons. So whatever side of the planet is tilted closer to the sun receives summer, and whatever is tilted away gets winter, and whatever doesn't gets spring and autumn. So the temperature on Earth varies, as we know. However, the lowest temperature we actually endure, probably not us as humans, is minus 88 degrees, whereas the warmest is 58 degrees Celsius. The planet has many layers and many features. The inner core is a solid sphere of iron and nickel, which reaches 5,426 degrees Celsius. The outer core is made of thick, viscous molten rock, which is where the layer of the Earth's crust rests. Our land is a continental crust, which is basically as thin as a piece of paper in comparison to the rest of the Earth's layers. It's that thin.
That's wild.
Yeah, we have valleys, mountains, and volcanoes, just like Mars and Venus. However, we have liquid water, which has 97% of our volcanoes and mid-ocean ranges in it. And there's a mid-ocean range of more than 64,000 kilometers long in it as well. The temperature of the Earth's surface is roughly 13 degrees. So that's just the surface. However, without our protective atmosphere, which is made up of nitrogen, oxygen, and carbon dioxide, a bit of water vapor and argon, it would actually be 0 degrees. Our atmosphere has a medium thickness, which also protects us from DNA damaging ultraviolet light reaching the surface, and it filters the heat that comes from the sun during the day and assists in retaining that heat when it goes down at night.
The fourth planet from the sun is Mars. The planet has a radius of 3,389 kilometers, which is only slightly more than half the size of Earth, meaning it's a lot smaller than Earth. Mars is 242 million kilometers away from the sun. It is also the most studied planet in our solar system. A lot of information is known about Mars. The oldest data taken by the Egyptians over 4,000 years ago. So that's pretty cool. In current times, a robotic spacecraft has been able to observe and explore Mars from all angles. Like Earth, Mars has clear seasonal changes in weather and climate. Mars orbits the sun in an egg-like shape formation, which causes the seasons to be much longer or shorter than the seasons on Earth. Mars is known to be the red planet because it is covered by brown, gold, red, and tan colors, giving it that red color from afar. The reason for these colors is because of the rusting of iron in the rocky landscape, which creates a distinct red dust, further adding to the red look of the planet. The surface of Mars is similar to that of dry land on Earth. There is water on Mars, but only in the form of water ice sitting under the planet's surface in colder regions. This is because of the planet's atmosphere. The atmosphere is extremely thin and consists of carbon dioxide, argon gases, and nitrogen. The temperature on Mars can range from 20 degrees Celsius and minus 153 degrees Celsius. The extreme cold is caused by heat escaping the planet due to the thin atmosphere.
Yep, so the fifth planet is Jupiter, and Jupiter is a very interesting and unique planet as it is twice as big as all the other planets, which we could see in our watermelon. Was huge, and it's actually as big as all of them combined. There is a distance of 779 million kilometers between Jupiter and the sun, making it the fifth closest planet. This planet is also known for its distinct stripe, and very large red spot. It is made up of hydrogen-based gases with a density only slightly greater than water. There are many differing surface features on this planet, which are the varying bands of clouds which spin in opposing directions. The dark bands are called belts and the white ones are called zones. These are caused by materials rising and lowering on the planet, which are due to the convection currents in the planet. There's actually no surface area on Jupiter. It is literally a giant ball of clouds that get denser and denser the more you descend into the planet. There is this great red spot on Jupiter too, which is due to the spinning of winds in so many different directions, basically forming a giant constant hurricane. This storm is so big, it is about 3.5 times the size of Earth. The temperature of the clouds of Jupiter is roughly minus 124 degrees Celsius. However, the center of the planet is far hotter, reaching 24,000 degrees Celsius. This is even hotter than the surface of the sun. And due to its elliptical path around the sun, the temperature of this planet is expected to be influenced heavily. However, as it is so far from the sun and has such a thick atmosphere, Jupiter stays very cold. The atmosphere stabilizes its temperature all year long, so it doesn't have any seasons. Another interesting fact is that Jupiter has a very rapid orbit, meaning its days are only 10 hours long. However, its orbit around the sun is elliptical, as I said previously, or oval-shaped, which means it takes 12 years to orbit. And the gravity is so much more intense on Jupiter, meaning that if someone who weighed, say, 45 kilograms on Earth, they would weigh about 108 kilograms on Jupiter.
Yes, our next planet is Saturn. Saturn sits just under 1.5 million kilometers away from the sun. What? Is that supposed to be billion? That doesn't make any sense.
Maybe.
That is supposed to be a billion, I reckon. That doesn't make any sense.
God won.
No.
Go.
All right, so our next planet is Saturn. Saturn sits just under 1.5 billion kilometers away from the sun. This is the second largest planet in our solar system. It has a radius over 58,000 kilometers and is 9 times bigger than Earth, but only 68% of the size of Jupiter. Similar to Earth, Saturn experiences seasons of ranging weather. Due to the planet's far distance from the sun, Saturn has an average temperature of minus 176 degrees Celsius. Weather can be extreme on Saturn, with winds sometimes as strong as 1,600 kilometers per hour. Saturn has rings around it that are made up of predicted comets, asteroids, or shattered moons. The ring system itself reaches out 282,000 kilometers from the planet. Saturn is colored yellow, brown, and gray, and like Jupiter, is filled with hydrogen and helium, meaning Saturn is a gas planet and therefore, unlike other planets, does not have a solid surface landscape, just like Jupiter. If it was possible and a human tried to walk on the planet, they would fall through the planet's center. However, from a distance, the reason why Saturn appears to have a solid surface shape is due to the hydrogen and helium atmosphere, which creates the visible texture of Saturn.
Yeah, wow. So Uranus is another interesting planet as well. It has been dubbed as the sideways planet due to its rotation on its side. It has a unique tilt, which makes it appear to orbit the sun like a rolling ball. One day on this planet is about 17 hours in length, and for it to make a complete orbit around the sun, it would actually take 84 Earth years. So seasons on Uranus are very unique, caused by its strange tilt. The sun will shine directly over each end of the planet for about a quarter of the year. However, this causes its other half of the planet to plunge into a dark 21-year-long extreme winter. It is a giant ice planet. Yeah, crazy. It is a giant ice planet that is almost 4 times as big as Earth. It is the 7th planet furthest away from the sun, with a distance of 2,873 million kilometers between them. Due to it being so far from the sun, the planet experiences harsh and freezing conditions all year long. And with its thick atmosphere, it remains very cold. So the average temperature of Uranus stays at around minus 197 degrees. So that's almost minus 200 degrees. And so the atmosphere around this planet is made up of hydrogen and helium and has traces of methane, water, and ammonia. And the methane is what provides Uranus with its blue tinge. And similar to Jupiter, it does not have a true surface, and like Saturn as well. It is a planet mostly made up of swirling fluid. So although there would be nowhere for a spacecraft to actually land on the planet, the dense extreme pressures of the atmosphere surrounding the planet would not allow any spacecraft to pass through and would actually just destroy it. Wow. It is extremely windy as well, blowing at 900 kilometers per hour, and it actually moves in opposite direction to the planet's rotation. So it's kind of just like going backwards on itself. However, so up on the poles.
I think this one's my favorite.
It's interesting, hey. However, on the poles, it starts to go the same direction. So it's literally one direction, another direction, and then the same direction. Weird.
Ridiculous.
Yeah.
Wow, that's crazy.
I like this one.
Very.
Okay, and then the last planet is Neptune. Neptune is the most distant planet from the sun, sitting at almost 4.5 billion kilometers away. This is more than 30 times the distance between the sun and Earth, so very, very far. Due to this distance, the planet is dark, cold, icy, and extremely windy. It's the coldest planet and the windiest of planets, which makes sense due to its distance away from the sun. The temperature gets to an average of minus 200 degrees Celsius, and the winds on Neptune are 3 times stronger than the winds on Jupiter, and consist of frozen methane flying around at 200,000 kilometers per hour, which is crazy when you think about the wind on Earth compared to that.
Mm-hmm.
Neptune also does not have a solid surface. It is made up of hydrogen, helium, and methane, so it is also a gas planet. Neptune is blue in color, like neighboring planet Uranus, who also has methane in its atmosphere, like we heard. Although Neptune is more of a brighter blue, and this is believed to be due to another unknown component in the atmosphere which impacts the brightness of the color. So they're not actually sure. They feel like it's something else
is in there
Wow.
that impacts the color that makes it even brighter than Uranus. So yeah, it's interesting.
That's so cool.
Wow.
That's interesting because we always learn in science how it's always like ever evolving and changing, and
Yeah,
we
so
don't
they
know what that
look
is.
at that one.
Yeah.
Yeah.
So basically, from all that information, we can see that there are many factors that influence a planet's climate and its seasons. So firstly, we can tell the distance from the sun is highly influential. The sun's rays will be much more intense the closer to the planet. And so planets which are further away, such as Uranus, are cold and harsh. The rotation time of the planet also impacts the climate. So if the sun is actually in the sky for longer, then half of the planet will become hotter compared to if it is in the sky for a short time. So just like Earth. Mercury, for example, has long daytimes, meaning it experiences high temperatures. And the composition of the planet's atmosphere also helps to regulate its temperature. So Venus has a very dense atmosphere, meaning it has little variation in its temperature, whereas Mercury has none at all, causing it to experience the full impact of the sun's rays. Another factor is the planet's axial tilt. So if a planet has a moderate tilt like Earth or Mars, or a large tilt like Uranus, there will be a distinct seasonal change in the length of day and night. For those planets close to the sun like Earth, its seasonal change will be marked by its two hemispheres, which we basically have on our very own planet. We've got the northern and the southern. And lastly, the orbit of a planet influences seasons and climates. So if a planet is more elliptical, I'm sure you heard that word a few times, it basically just means it orbits in an oval shape around an object. So there's going to be far more variation in temperature as it orbits the sun because it's elliptical.
Right.
Yeah, and so that's it. So Alicia, I think it's time for us to do our final hypothesis.
Yes. Wait, was that going to be
Do we
after
maybe
results?
want to look at the
The results.
data
Oh, sorry.
and some
Sorry.
graphs?
So now that we've heard all of the CDSU, I think it's time that we pass it over to Jenna so she can show us the data graphs and stuff like that with the real information.
Yes.
Jenna?
Nice.
All right, let me just share my screen.
Excellent. Very exciting.
Okay, can everyone see my screen?
You can.
Okay, so in this first table here, we just have our predictions versus the correct fruit. So we can see we did get quite a few right as we discussed, apart from the lime and the apple.
Yeah.
We just mixed
yeah.
around. So that's quite interesting. That can be an interesting activity, especially to do in the classroom, getting kids to predict it, write it down, and then showing them the correct answer and seeing if it correlates.
Yeah. Comparison.
Yeah, I think doing a graph for this one is a little bit pointless. I don't think it really shows us any patterns. I think the table is just good for showing the comparison to see if it's right or wrong with your prediction. What do you guys think?
Yeah,
Totally
definitely
agree
agree.
on that.
Yeah, there's
Yeah.
no sort of real data there. It's more just us observing.
Yeah,
Yeah,
just let them
exactly.
see what we said, and then the real.
Yeah,
answers.
yeah,
It's
exactly.
good for like students to go back and have a look at what they thought was right, and then after see how they've learnt and grown.
Yeah,
Yeah.
definitely.
So this next one, I think a bar graph really represents and shows the predicted distance versus the actual distance quite well, especially having
Yeah.
the two different colors.
That's great.
Makes it
Now,
stand out.
Yeah, it
Oh.
shows you how close you were. Now, we need to keep in mind that this isn't very accurate. As we can see, it looks like we got it exactly right here, but we were, 0.1.
We already knew that one.
Right.
Whatever. Yeah.
So, we did already know that one. But so just when we think about what numbers we're using on our Y and X axis, that's super important because students can think,
Yeah.
oh, I got it spot on, I'm right.
Oh, I see what you mean. Yeah.
Yeah,
So it was
but-
30 and then 30.1, but they look exactly that. Yeah.
Yeah.
Cool.
Yeah, so
Totally.
30 and 30.1 look exactly the same. And
Yeah.
so making sure we think about what we use on our Y and what we use on our X
Yeah.
is very important.
Definitely.
Yeah, so, but I think that this graph here does give us a nice comparison to see our predictions versus our the actual distance. And from this graph, we can actually see that our predictions were a lot lower than the accurate scaled down version, so in meters, which is quite interesting. So we said 5 meters, whereas it's 0.38. So
Quite a,
we
quite
were
a bit
so
of a change
off.
there.
yeah, so
So
that's pretty
off.
crazy. And like we even see that 7 meters or 0.72,
Oh,
10
that's
and
yeah,
1.
wow.
Yeah,
It's
so
interesting
we
when you
are,
saw it out on the field as well, in the park and everything. It just
Yeah.
looked like you could see how off we were along that massive
Yeah.
scale.
Yeah,
Yeah.
absolutely. So yeah, I think this graph really does show our predicted versus accurate quite well.
Yeah.
Then as we kind of got further out, we did get closer. So in
Yeah.
like 19.2 is the actual distance versus 28 for Uranus. And then Neptune, we already knew that would be 30. But we were on all of them very low,
Yeah.
which is
Yeah.
quite
I was
interesting.
just going to say as well, sorry to jump in. I was just going to say as well, it was interesting because when I was out in the park as well, I actually left the estimates out on we didn't have to, but I left them out there so that we could see the difference as well. I put the others because it's so interesting to see the comparisons, not only in a graph, but also like in real
Yeah.
life as well.
Yeah, it's a
So
nice sort
I
of
definitely left them out there.
progression. Yeah, like a nice progression, obviously, to introduce it in like really hands-on way. Before, if we just jump straight to this, the students might be a bit like, oh,
Yeah.
what does that even mean? So they got to see it, got to do it, now get to show their understanding this way.
Yeah.
Totally.
Well, I think maybe a pattern with our prediction was that we actually spread them out quite a lot. So we spread out the planets more than they actually are. So that's a pattern in our prediction. Whereas you can see like these are all very close together, and then we have a jump.
Yeah.
Yeah.
So that's pretty interesting. All these so close together, all within 1 meter, and then it
Seems
goes
to be like
5 meters.
Yeah, it seems like the first 4 are like, because I think, didn't we say in the CDSU that it was like the first 4 were rock, like, or they had like a core, or they were solid. And so you could see that like the first 4 there, maybe that's why, or there's a pattern there. That's why they're smaller and closer.
Yeah.
As they're gassy, they get further out.
Something to
Yeah,
think
they
about.
get bigger, don't they? And they form in gases. They're no longer ice or formed.
Yeah.
Are they?
It's more expansive, or that's why they're bigger or something. I don't know. Very interesting.
Yeah.
And so with this
Definitely.
graph as well, obviously I'm going to go in and put in the planet names and a title.
Definitely.
But just because we've done it during the experiment, I didn't want to take up too much time. So I'll go in and put in those names afterwards.
Yeah, too easy.
Okay, so the next one is about the planets in the solar system and their characteristics. So I have all the planets in order here, and then their distance in millions of kilometers, and then their minimum temperature and their maximum temperature. Now, I found this super interesting when Alicia and Darcy, you guys were talking about it. I think I had the idea in my head that the planet closest to the sun was going to be absolutely the hottest.
Me too,
So I found
absolutely.
that
Yeah.
so I found that really interesting. So I wanted to record that. I think this, including the distance from the sun in our graph, can be a bit confusing. As this is in millions of kilometers, and then this is in degrees, where it's like only going.
Yeah, it'll get too messy.
It's too messy. It'll be really big on top and then really tiny down the bottom.
Yeah.
Where our degrees are.
I like how you've done it
Yeah.
like this. It's just a really nice way of displaying it in a really simple way.
We are.
So
Yeah,
I
no
can
need for a
show
graph.
you- I might just show you that because it I did have a try, and it just it doesn't depict the pattern that we're trying to look at.
Yeah.
Right,
And they're meant 2 different, like the independent and the constants, like they're different measurings altogether. They're not in the same units. So
It's very hard to read, especially for like grade 5. Like imagine. it'd be-
Darcy, so you recommended a line graph. Let me try.
Oh yeah, possibly. Okay.
It's still.
Well, it
got
does
the
give you the
weird
3 separate.
unit,
Yeah.
That is a lot
I feel
better.
like you really have to reiterate, like, don't forget they're in different measurements. It's not all, kilometers.
Yeah, that's where it
Yeah.
gets messy, I suppose.
yeah,
And you
definitely.
can't really tell the minimum value down here.
No, it's not succinct enough
you're
or
not really
detailed
getting
enough.
the picture.
Yeah.
You don't
We
know the
prob-
actual minimum values.
Yeah.
So what I thought would be better, sorry, I'll just get rid of that, is to do without the distance and just
Yep.
have them in order. So have the
Right,
planets in
yeah.
order from closest to the sun to furthest away.
Oh, great. Yeah.
And temperature. And
Love
now
that.
I chose to go with this graph. So like a horizontal bar graph, so that
Yeah.
you can see the negative values more clearly.
Yep.
Yeah,
Yeah, a
definitely.
bit of a
Like that.
timeline sort of.
Yeah, exactly. Yeah. And so it's interesting here how Venus, because they were they didn't have any maximum values. So Saturn, Uranus, Neptune,
Mm.
they didn't have maximum values. They are at a quite constant temperature, which Darcy and Alicia were saying. So they don't
Yeah.
have any maximum temperature. And I kind of find interesting Venus is all in the positives, whereas
Yeah.
all the other
Oh.
planets go into the negatives.
Can go into the negative.
Yeah, so that's quite interesting.
Yeah, it's a cool pattern.
Yeah, I think I will change this graph maybe to have more specific measurements down the bottom.
Sure.
Yeah.
Yeah,
I think that would be
Ac-
beneficial
bit more
rather than going
accurate.
0 to negative 200. Like, what are
Yeah.
all these?
Yeah.
So
Agreed.
maybe going up in like 5s even
Yeah.
would be really beneficial, I think, just to really see. But I still think, yeah, this type of graph does depict the pattern that
Yeah,
we're
definitely.
seeing.
Yeah, no, it does.
Yeah, I like the way that you've shown that.
Yeah.
Definitely.
Maybe you
I
could
like
like change the colors. Could you check like you could do it like below, like blue or something to make it cold or whatever.
That's a
Yeah.
great
Just for
idea.
kids, you know.
Yes. Yeah, that's a really good idea.
Yeah.
I like that.
Yeah.
So that
But,
they're
like-
not maybe it makes it a bit more obvious.
Yeah. So I think I had the misconception that I thought, Mercury would be the hottest and
Same for
wouldn't
sure.
go into the negatives as much as the others.
Yeah.
And it would kind of be this stepping building block
Yeah.
looking graph, but it really doesn't look like that at all. It really jumps around. So that's really interesting.
That's
I
so
think.
true. I did the same. I would just think that it would have gone from 1 to 7.
Yeah.
Like
Yeah, sort of
getting
progress.
colder as you go in like an order. So
Yeah.
yeah, that's interesting.
But yeah, as it goes away,
Like-
it'll just be this like straight increase, just pretty
Yeah.
even.
Well, it's interesting too because I suppose we're looking at the planets in a row, right, for educational purposes. But realistically, they're all going to be
Yeah,
orbiting in their own thing, and so that's why there's those variations. And that's something cool that we picked up from CDSU and the graphing. It's
Yeah.
because they've all got their own separate ellipticals or oval shapes or whatever on their axis. There's the cool old Uranus on its little roly-poly. So I just
Yeah.
think like that's so interesting that you can have a graph that sort of indicates exactly what we've
Yeah.
discussed. It's really
Yeah.
cool.
Definitely.
And yeah, I really like your idea of having the minimum temperature as blue.
Yeah,
I
related
think
easy.
back.
that's really helpful, especially
Yeah.
because orange, like I kind of think orange is hot.
Warm, yeah, sort of.
Yeah.
Yeah.
Yeah, so that can be confusing for students. So yeah, making like that blue and then the other side yellow or orange or whatever. I think that's a great idea.
Yeah.
Yes, I do agree with
Cool. So Darcy and Alicia, I'll hand it back to you. I'll stop sharing my screen.
Okay, so now we can move on to our final hypothesis. So from our observations from both the investigations and activities, we can use our inferences to formulate our final hypothesis. Even though we didn't have initial hypothesis, because this was obviously more of a modeling activity, we can still formulate our final one based on information that we've learnt now. So Darcy, do you want to take that one?
So from all the CDSU, our observations and obviously our inferences we make from the CDSU, I reckon we should say something like the climate and seasonal change on planets in our solar system can have many variations due to factors such as distance from the sun, thickness of the planet's atmosphere, its axial tilt and orbit around the sun. Does that sound good to everyone?
Awesome.
Yeah, I
Yeah,
think
That
that pretty
nails
much
it all.
covers everything.
I'll write that one down then.
Yeah, that's great.
All right.
Excellent.
And just
Okay.
thinking about the results again, sorry, those things would be a good thing to include when we're looking at results. Like I know we just did temperature, but in like having a look at, its axial tilt, orbit,
Each one.
thickness of its atmosphere, that all could be incorporated as well, I think. To see a
Totally.
clearer picture.
All right, so that sort of ties us over into our left-hand sort of side in terms of, you know, things that we've learnt this week from our experiment. So compared to last week, we decided we're going to do an infographic. So one thing sort of in particular that we learnt this week was in regards to like technology. Obviously with the nature of this experiment, there was some really great use from our facilitator, Beck, who really got in there. She showed us lots of different camera angles so that we could fully see. Because obviously you know, like at this point in time, we are in circumstances where we can't all meet together as a group. So we have to make, you know, the most of our technology and use it to the best of its ability. Also, we decided to use the Canva program, which is quite a useful platform. So it's super easy for us. We all got to jump on there. Everyone can see it. It's a shared document. So everyone can sort of, you know, each contribute their own part as they go and work on it over the time when it suits them, so that we don't all have to be together when we're working on it. So with our Canva, it was a really engaging and effective tool. So sort of finding our creative side to display the information, because obviously we can, you know, use everyone's strengths, you know, in terms of some of us prefer the written text. So we had a little couple of blurbs in there, whereas some of us prefer pictures and sort of animation kind of things. So it's a nice way to sort of present that in an all-rounded way.
Yeah. I think like one of the main reasons I suppose that we chose to do an infographic this week is because it provides an effective way for students to create a snapshot of the science content and pedagogy covered in this week. These in the classroom could be displayed as a reminder for future reference or to correct any misunderstandings.
And like being the facilitator this week, it was really important to make decisions regarding the resources and to be aware of students' access to such objects as well, I think. So in this instance, we had to adapt to suit our environment. We've sort of had to chop and change a little bit and get outside. And we had to suit our environment with filming space and materials. But in some cases, not all students will be able to bring those items to school, I think. And it'd be best to assign maybe one material for each group member to relieve the pressure. A family's feeling the need to buy materials when the experiment can be adapted to suit what they already have. So, you know, using the watermelon was great. You could use a softball, really.
And like
I think with this one, the relative sizes was good for activity one. But realistically, in the second activity, it really wasn't that necessary to have the relative sizes. We could have used just cones or something like that. So it's okay to, I suppose, chop and change it and things like that to suit everybody. But we can talk about that more on our left-hand side this week.
Yes.
Yeah, definitely. I think there's some good points there.
Nice. All right, guys. I think that's us for the week. Really stoked, really happy with how everything went. Anyone have any questions or last things they wanted to pipe in?
That was a really interesting activity.
Yeah,
I learned
definitely.
I learned a lot too.
Yes.
My new favourite planet, Uranus. Love it.
Yes. Awesome.
Love it. All right, guys. It's been a hoot. Have a great week and we'll talk soon.
Definitely.
Yeah, for now.